Appreciate the invitation for presenting, and thanks, Michelle and Melissa, for setting this up. So what I'll be presenting is a study. It's an ongoing study, which is called Temperature-Related Mortality under Climate Change Scenarios in Health Regions of Canada. And what I'd like to acknowledge before going into any details is the contribution of the people who have been involved on this study so far. So several colleagues from Health Canada, Christopher, who played a central role in this study, and several other colleagues from Health Canada as well, and also some colleagues from the London School of Hygiene and Tropical Medicine, and colleagues from Quebec, and as well as Melissa, who was involved on this study. So this is the outline of today's presentation. I think we all agree that climate change is recognized as the biggest global threat of this current century. We know that the IPCC established that anthropogenic emissions of greenhouse gases represent the dominant cause for the warming of the planet. In Canada, since 1948, for some report that was published recently, was established that temperature increased by about 1.7 degrees Celsius in Canada. And it's expected that in the current century, up to 2100, we might see an increase on average by about 5 degrees Celsius in major cities under a high-end greenhouse gas emission scenario. So future greenhouse gas emission scenario or future emissions will affect increasing temperatures, and therefore the trajectories in terms of where we will be going in terms of emission scenario will likely affect future health impacts. So the idea behind this project is that we hypothesize that future increases in surface temperature in Canada will result in increases in mortality events due to non-optimal temperatures. There's been a number of studies that focused on projecting the health consequences. So projecting meaning that if we're interested in knowing what would be the future impacts, we are interested in knowing based on greenhouse gas emission scenarios in the future, what would be the temperature increase that we would see, and then what would be the impacts on health. And so there's a number of studies that have been published in Canada, in the US, and also elsewhere in the world. And there's still some sort of debates that remain regarding whether the increase in heat-related health impacts would be offset by a decrease in cold-related health consequences. So in other words, if we see perhaps more warmer temperatures, well, we might see also a reduction in cold-related temperatures, but will those be sort of balanced out? So there's still sort of an uncertainty in that regard. A few years ago, some of you may have seen this study, which we did with an international group, which was led by one of the researchers who's involved in this current study in Canada. But this study looked at projections of temperature-related excess mortality under different climate change scenarios, but as a global picture or across different countries. So those are the locations, the cities that were included in the analysis. What you see here is a map of 451 locations, mainly urban cities, where we had data on temperature for historical periods, and where we projected the future temperatures based on different climate change scenarios, and we projected the potential health impacts in the future. And in this map, what you see here is the average daily mean temperature for those locations. So obviously the colder or northernmost location, the daily average is sort of the coldest. And this is just a map basically to show you the locations that were included in our previous study. And what we found in that study that was published in 2017, if we look specifically at North America, which included Canadian cities, about 26 cities in Canada, and also several cities in the US. There's different lines here that represent different sort of trajectories of temperature increase based on different climate change scenarios. So you may be familiar with the different RCPs, the RCP 2.6 being the sort of the lower emission scenario, and then the RCP 8.5. So therefore, what we found, just looking at a descriptive picture, is that the increase in temperatures will be quite important in a scenario of high emission greenhouse gases, as opposed to a low emission scenario. So those lines are for North America, for all of the cities in Canada and in the US. And what we were really interested to see is the future impacts of heat and cold based on those different scenarios. So at the bottom are some of the different scenarios. In today's presentation, what I'll do is I'll often make comparisons between the RCP 2.6 and the RCP 8.5, which are sort of the two opposite scenario. Again, this one being the low emission scenario and this one being the high emission scenario. And in the end, what we found is that this red line and this blue line represent the heat-related excess mortality and the cold-related excess mortality. So under a low-emission scenario, we might see still a little increase in heat-related mortality, and then under a low-emission scenario, we might see a little decrease in cold-related mortality. But then, if we look at the high-emission scenario, we found that the increase in heat is quite important and is not really being offset by this decrease in cold-related mortality. And this is sort of the findings that we got from all the locations that we investigated in our study. And in this map here, you would see the heat-related impact across all locations that we investigated. And in this case here, the cold-related impact in terms of reduction of cold-related mortality. Now, what we really wanted to see is that net impact, whether that decrease in cold-related mortality might be sort of offset or might be balanced out by the increase in heat. And what we actually found is that it's really small, the difference under a low emission scenario, but under a high emission scenario, we found that for North America specifically, so for Canada and the US, we found that there would be towards the end of the century, so that is in this case here 2090, the last decade of the current century, we would likely see more heat-related mortality, and this increase is not being offset by the reduction in cold-related mortality. So this is just to sort of put things into context as to why we did the current study only in Canada. So again, this is a map just showing all of the locations that we investigated in the study. And for Canada and the US, we have here an idea of the net change in excess mortality. So overall, we see that for most locations in North America, we see about an increase of 0 to 5% of excess mortality towards the end of the century based on the high emission scenario. But one thing that I found and we found is that in the previous study, we looked at non-accidental or all-cause mortality, and there's still a lack of understanding on the projections of health impacts on cause-specific mortality. For example, cardiovascular, respiratory disease, which represent an important burden on the healthcare system. And there's also a lack of understanding on how the future temperatures might impact morbidity, so in terms of hospitalization and emergency room visits. And most of the studies that have been done so far have been focused on urban areas. And therefore, rural areas are also of importance in terms of understanding the future impacts. So the objective of the study findings that I will be presenting to you today will be specifically on evaluating the projections of temperature-related excess non-accidental mortality, but as well on cardiovascular and respiratory mortality across health regions in Canada. So I'll focus this presentation mainly on mortality and cause specific for these two main causes. But as I will mention towards the end of the presentation, there are ongoing research that we are conducting in looking at morbidity. So this study that was put forward maybe a year ago, it's called the Canadian Temperature-Related Excess Mortality and Morbidity Projection. And it's really a time series epidemiological study design that includes projection models. And time series data mean that we have, on a daily basis, we have count of mortality events and average temperature for health regions of Canada. So there's, right now, there's currently about 111 health regions in Canada that sort of represent different public health units across the country. And the data that we got was for years 2000 to 2015. So for each health region, this is a map of all of the health regions that we have in Canada. Obviously, for some of the more densely populated areas, like in southern Ontario, the health regions can be quite small. But as we go further north, the health regions are quite large. But for each of those health regions, we had daily data for years 2000 to 2015 on the number of mortality events and also on the daily average temperature and the average humidity during that day. So the main exposure is temperature data that we got from Environment and Climate Change Canada. For each health region, there's a number of weather stations that are operating in those health regions. Obviously, some health regions don't have the same numbers or a dense network, but each health region across Canada has at least one weather station. And we use that information, and we got the mortality data from the Canadian Vital Statistics database in order to get the information on non-accidental cardiovascular and respiratory mortality. So then the other aspect to this project is also getting projections of future temperatures. And those projections were obtained from a database that has sort of global simulation of meteorological variables. And we used that data set in the previous paper that I showed you earlier. And this data is based on different climate models under 4 emission scenarios. So again, the different scenarios are based on concentration pathways of greenhouse gases. So RCP 2.6 based on the low emissions. So if we drastically change greenhouse gas emission to a minimum, and the RCP 8.5, which would be a high emission scenario. So we got temperatures based on those different scenarios up to year 2100 for each of those health regions. And the data was downscaled to a fine level resolution, and we applied something called a bias correction so that the historical data that we had and the projection data could match up appropriately. So then in terms of statistical analysis, I won't go into fine details here, but this type of study has been done in previous research, where what we do is a first stage, we run a regression model called a quasi-Poisson regression, and we look at the short-term effect of temperature on the number of mortality events for each of the health regions, and we take into consideration a number of factors in our regression models, which are outlined here. And then we run a multivariate meta-regression to obtain an overall effect of the impact of temperature on mortality. And then what we do is that we project the impact in the future. So based on the projection of temperatures in the future, we are able with those methods to project the future impact of temperature on mortality in terms of percent excess mortality. So percent excess mortality, you will see in the tables I'll be providing that the way that the findings are shown is in terms of how, what is the percentage of all mortality events that are due to either heat or cold or the overall contribution of temperature. So this is the approach that we used, and this is a validated approach that was published in this paper by some of the colleagues that are involved on this current study. So in terms of results, first of all, this is a graph showing you the temperature trends by different scenarios in Canada. So what we see here is compared to this baseline decade, which is the decade of 2010-2019, we are quantifying the increase in temperatures across the country, so the average increase across all of Canada based on the different RCPs. And what we see is a similar pattern to what I showed you earlier, in the sense that we see an increase in temperatures under the low emission scenario, but under the high emission scenario, we see this quite important increase up to about 2090, 2099, which is sort of the last decade that we looked at in our projection. And in terms of looking at individual health regions, in terms of projections, when we compare decade 2090, 2099 to the decade of 2010, 2019 under a high emission scenario, we sort of get this map here of the different health regions across the country. And what we see is that most health regions will have an increase in temperatures based on the different color coding that we see here. But there seems to be a pattern where northernmost regions seem to be suffering mostly for this increase in temperatures, which is not something new, because this has been reported before in previous studies. Those are descriptive statistics of the historical data that we used. So the data for 2000 to 2015 for each of the health regions, the average values that we obtain. So the average temperature across Canada for all health regions included together is about 5 degrees Celsius. And when we do a comparison of 2090, 2099 versus this decade, we see that the increase in temperature under a low emission scenario is about 1 degree Celsius. But then if we go to this high emission scenario, we see this increase of about 5.6 degrees Celsius. And this is the range in terms of min and max across the different health regions. So under a high emission scenario, the lowest, the minimal increase will be about 4.5 degrees Celsius, and the highest increase will be about 7.7 degrees Celsius. And this is just the data that we used in terms of the all-cause cardiovascular and respiratory mortality data, the number of events that we had on average per day in across Canada. So here I am presenting the impacts of heat, of cold, and the net impact in terms of excess non-accidental mortality. So when I am referring to heat and cold, it means extreme heat, extreme cold. And the net impact is that overall impact, considering heat and cold together. And so in this table here, we have 3 decades that are being reported. So decade 2010, 2019, 50, 59, and then 90, 99. So I'll be mainly focusing on the one towards the end of the century, just to show the sort of pattern of the projections in the future. And what we are seeing under this low emission scenario, this RCP 2.6, is that the net impact in terms of excess non-accidental mortality will be really null, because the confidence interval here overlaps the value of 0, which is the null value in this confidence interval, and therefore the findings are sort of not statistically significant in the sense that there doesn't seem to be a difference in terms of excess mortality in 2090-99 compared to the decade of 2010-2019. But if we look at the high emission scenario, we can see that the contribution of heat is about 5.42%. So it means that 5.42% of all mortality events should be attributed to heat, and about 1.6% should be attributed to cold. So overall, the net impact when we compare this decade to the decade of 2010-2019, we see an increase of about 3% in excess mortality. And the findings for cardiovascular mortality are reported in this table here. Again, we are seeing a similar pattern in terms of a low emission scenario. There doesn't seem to be much difference in terms of excess mortality, in terms of cardiovascular mortality on a low emission scenario. But then when looking at the net impact in the future, in decade 2090-99, we see this increase of about 2.34%. And finally, this table presents findings for respiratory mortality. And respiratory mortality is showing a similar pattern again for this low emission scenario, where the impact is really negligible, but this impact in the future on respiratory mortality seems to be really, really important. Heat seems like all respiratory mortality events, there seems to be here about 12.6% that are due to heat across the country, across Canada. And then the contribution, the overall contribution of heat and cold taken together, because there's a likely reduction in cold impacts. As we can see here, the impact of cold in decade 2010-2019 is about 2.90, and then it drops to 1.94, and then towards the end of the century, it drops to 0.8. And so basically, this number here is the net impact compared to that current decade of 2010-2019, and we are seeing this 7.8% increase in excess respiratory mortality. And when looking at specific health regions, this is a map showing you the regions across the country. Not all regions are have a dot, because some of the health regions had really small numbers in the analyses, and therefore it was difficult to obtain a valid estimate. But what we are seeing is sort of an increase in the excess mortality. So that's for excess mortality, including cardiovascular, including respiratory. And we are seeing these dots across the country showing these increase. And a pattern that we found was that in the coastal regions, the excess mortality, the percent excess mortality, doesn't seem to be the same extent to other locations, and it seems to be a little bit smaller. So the main findings so far have been that we found a net increase in temperature-related excess mortality in the order of 2.96% overall for Canada under a higher emission scenario. And there doesn't seem to be marked changes in the net difference in excess mortality under a low emission scenario. And then when looking at the net impact of excess cardiovascular and respiratory mortality, we see this net impact of 2.34% for cardiovascular and this 7.8% increase in respiratory mortality under a higher emission scenario. So in looking at those findings, we can conclude that climate change may potentially result in an increase in heat-related excess mortality that is not balanced by a decrease in cold-related death. And the results, this results in an overall positive net increase in mortality for Canada. And the findings that we obtained generally agree with those of our previous study, the study that I showed you earlier, where we included in a number of urban areas across Canada. We included 26 cities across Canada in that global study. Although the projected net increase for Canada was 1.9%, and now we got this number of 2.96%, which is higher, but we included in our current analysis rural locations and a much broader picture than just looking at those 26 cities. The other thing also is to say that other reports, whether in the US or China or Europe, have reported contradictory findings, in the sense that some studies are saying that for some countries, the projected excess mortality due to temperatures might not be an increase even under a high emission scenario. So it could depend on a lot of factors, but for Canada, it seems to be the case. It seems to be showing an increase. For example, a study conducted in China also found that temperature-related cardiovascular mortality would increase under higher emissions. But another study also done in China found that temperature-related ischemic heart disease mortality would remain stable under a high emission scenario. And to our knowledge, so far, there hasn't been any study looking at the projections of temperature-related excess respiratory mortality, and therefore it's difficult to do any comparisons in that regard. We have a number of limitations in the study. We did not account for demographic changes over time. We didn't account also for potential adaptation to future temperatures. There's also some uncertainties in the climate models that were used, although they've been used before and validated. And there's, of course, some misclassification bias of exposure to temperature due to the fact that we use ground weather stations for the historical data. But it's a large-scale EPI study done across Canada. We're using validated methodological methods, and we are including urban as well as rural areas, which is a very important aspect in terms of having a national picture of future impacts. So in terms of conclusion, the findings of this study suggest that Canada will experience an increase in mortality due to non-optimal temperatures under higher greenhouse gas emission scenarios. And the findings have important implications for climate policymakers. And that's why we did this study, because it could also have impact for public health officials that want to know what would be the future impacts in their communities. We have some ongoing research based on this study. We are interested in looking at temperature morbidity projections under the different climate change scenarios and being able to associate those impacts to potential healthcare costs in the future, mainly focusing also on some important cause-specific hospitalization, such as cardiovascular respiratory disease, but also important outcomes such as mental health and other important outcomes that could be related to the short-term impacts of temperature. We are also interested in accounting for demographic changes, having information on future demographic characteristics in each of those health regions. So we're working with Statistics Canada to get this data and being able to account for this important factor into our future analyses. And there's also interest in looking at perhaps projections of future air pollution impacts, because we know that, for example, ozone in some of those regions across Canada may there may be an increase in ozone, and we are already seeing increases in ozone in some of those regions. And this is a list of references of some of the studies I just mentioned today, if you want to have a look at those studies, and I'm happy to answer questions. Thanks.
All right. Thanks, Eric. So we do have a couple of questions here in the chat box. And again, please go ahead and add your questions in here and I'll read them off for Eric. So the first one, what was the data source for daily mortality on heat-related mortality in Ontario Health Region?
So the data source was, well, it was data from Statistics Canada. It was the Canadian Vital Statistics database. And as an employee of Health Canada, we have a data sharing agreement with Statistics Canada where we can have access to some level, individual level data, and then we aggregate it. And by individual level data, I mean there's information on diagnosis and date of death, and a few additional information like age and sex, but obviously there's no personal identifiers. And this data was used to aggregate the data on knowing the number of mortality events per day for each of those health regions.
Okay, thank you. The next one, it asks about how you measured the net impact. So you showed a couple of slides that showed the net change in excess mortality. How was that measured?
So, for example, this slide here, let's say that we look at this number here, the respiratory mortality impact. We basically quantify the number of mortality events that are due to either heat and cold for this decade, 2010, 2019, and then we quantify the same impact for 2090, 2099, and then we quantify the increase in mortality that are due to heat and cold for this decade, and look at the percent increase. What would be the percent increase of mortality that are attributable to heat and cold for this decade compared to this decade here. So this is why in the column 2010, 2019, you would see that there's just nothing being reported in those cells here, because we basically, this is the baseline decade, so we cannot say anything about comparing 2010, 2019 to that same decade. And so therefore, when we look at those numbers, this one here, we are always sort of quantifying the percent increase in mortality due to the contribution of both heat and cold together.
Right. So the next one, how do you determine projections for individual health regions, given that some are larger than the 0.5 by 0.5 degree grid?
Yeah, so the grid is available on a global basis, and the what we did is that for the historical period, we had only the ground weather stations that we got the data from. So for the future temperatures, what we did is we used those ground weather station locations, so the lat and the long coordinates, so the geographical coordinates, and we got the temperature projections for those specific locations so that they could match the exact locations that we used in the historical period. And therefore, the 0.5 by 0.5 grid, we basically used the average of all the weather stations. So for example, if we'd be looking at the region, the Toronto Public Health Unit, which is a specific health region, we would be looking at several weather stations across the city of Toronto, and we would look at the specific projections of temperature for those locations in the future. So you might think that yes, it is limited because we're not looking at temperatures everywhere across the health region, and that is sort of a limitation, but we wanted to match the future temperatures based on the weather stations that we use. But maybe a future analysis that we might do is we have access now to historical satellite data on previous temperatures, and therefore we might be able to use perhaps the whole health region level of temperature projection.
Okay, thanks. So you did mention ozone. There's one question here that asks, what is the health link to ozone?
So ozone is a respiratory irritant. Ozone has an impact on the respiratory system in terms of short term. When ozone increases, people, especially those who are vulnerable in terms of like having respiratory morbidities, can suffer from the increase in ozone. And in that regard, it is important to look at the future impacts of ozone, because if ozone is associated with some increased, because ozone has a clear link with temperature. Ozone is formed in, especially on like a sunny day, when there's heat, and as well as other outdoor air pollutants. And therefore, if we anticipate that there might be more ozone in the future in some regions, may not be the case for all regions, but some regions may have increases in ozone, then it is important to know what would be the future impacts. And again, that might be mainly on the respiratory side of things, but there could also be links with other health systems as well.
Yeah, so we have a related question, and you just touched on that a bit. The question was, with the aging population suffering from comorbidities, so respiratory and cardiovascular diseases, for example, are we able to account for those excess mortality, respiratory and cardiovascular diseases?
Yeah, I think honestly, it's a very good question, and it's a very good suggestion of when I mentioned that it is going to be important to understand perhaps the future impact based on hospitalization. It might also be important to account for comorbidities, and there are some ways that we could account for that, but it is something for future research, because it is something that public health units and also national climate policy makers would want to know in terms of what would be the future health impacts and the future costs, based on the fact that some people might have a specific comorbidities. It might be more vulnerable to the effects of temperatures.
Okay. So we have about 3 more questions here. How are you defining heat and cold in your study?
So in that study, it was defined as the 97.5th percentile of each health region. That level was defined as heat, and the 2.5th percentile of temperature distribution was defined as cold. So for example, let's look at, again, maybe the example of Toronto. If we look at the example of Toronto, we have data for years 2000 to 2015. And so for that period of time, we looked at what's the distribution of the temperatures in the health region of Toronto, and what is the 97.5th percentile. So for example, the 97.5th percentile of temperature could be around 30 degrees Celsius. And that 30 degrees Celsius was defined as an extreme heat. So when we looked at the impact of heat, we compared 97.5th percentile to the minimum mortality temperature, and the minimum mortality temperature is specific to each health region. It's that temperature for each health region where we see a minimal impact of temperature on mortality. Usually in Canada, we see this at around 15 to 20 degrees Celsius. So when we compared heat, we compared the 97.5th percentile to that minimal mortality temperature, which is around, again, 15 to 20 degrees Celsius. And for cold, again, this was specific to each health region. Toronto might have a, say, minus 15 of a 2.5th temperature percentile, but maybe a northernmost health region might have another 2.5th temperature percentile. So that's how we define extreme heat and extreme cold.
Okay, and did your mortality data classify cases as heat or cold, or were they determined based on daily rates and daily temperatures?
The mortality data was basically reported as the number of people who had specific diagnosis codes. So it was not reported in the mortality database whether heat or cold was causing the event. It was really in the mortality database, we used ICD codes, so International Classification of Disease. And those codes would mention whether it's a cardiovascular mortality or respiratory mortality or any other types of mortality events. And that's how we got the information. So obviously there might be some mortality events that are not due to heat. And this is why when we did our calculations, the slide where I am referring to attributable mortality, the way we do our stats is that we are able to quantify among all cardiovascular mortality, what is the percentage that is specifically due to temperature. And this is what we are seeing with those 2.34%, for example, for cardiovascular mortality.
All right, thanks. And last question here, were disease projections, or what disease projections have been considered?
Well, so far we considered only the cardiovascular and respiratory mortality, but we are interested in looking at other mortality events such as renal disease, diabetes, COPD, asthma, and also interested in looking at projecting the impacts of future hospitalization on some of those similar outcomes that I just mentioned, and also mental health. So those have been identified based on the previous knowledge of how we know temperature might affect different organ systems, and the ones that I mentioned are the ones that we are interested in.
All right, thanks. So those are all the questions we have. Feel free to reach out to myself or Melissa or Eric for more information. Again, this is a webinar series that we attempt to do quarterly, focused on extreme temperature. So apologies for the technical difficulties early on, but thanks for hanging in there with us. Melissa, I'll hand it off to you to close us out.
Yes, so I just wanted to echo everything that Michelle said. Thank you very much, Eric, for taking the time to present to us today. And thank you everybody for attending. And as Michelle said, don't hesitate to reach out, and we're going to attempt a little bit better on our quarterly moving forward. So thanks everyone once again, and hopefully we'll see you again in a few months.
All right, thanks, bye.
Bye.